your entire screen. I see the screen here. You're presenting to everyone, but I don't know what you're getting.
Able to see your now just maximize the PPT, sir.
Sir, you
Maximize the PPT. Click on the PPT that is open.
I have done it, but there's no PPT here.
Sir, in the bottom you can see the
Bottom in the
presentation.
taskbar you can see, sir.
Yes, sir. Yes, sir. Yes, sir.
Yeah.
Yes, sir.
Okay, got it. Okay.
You can go into slides. Yes, sir. We can see.
Yeah. Okay, thank you so much.
My pleasure, sir. Thank you.
Sure, no problem.
Okay.
Yeah, it's a bit early in the morning for many people. I don't know. Not all of them are used to, be ready at 8:30. After I left IIT, this is the first time I'm giving a lecture before 9:30 or 10. IIT, I used to prefer, 8 o'clock lecture. So I was the first one. Nobody would like 8 o'clock lecture, even the student, but they would come. And once I finished my lecture, the rest of the day was mine. But if you have a lecture at 10, 11 o'clock, you don't feel like doing any work till that time.
That is correct.
You always think of what to present or what to teach. So 8 o'clock class is the best. Only in India we have this late starting, the British culture. One country which starts work very early, Norway. They start working from 7, even in winter. They want to finish the work by about 3 o'clock. And they say we'll have a lot of evening to spend with family, children, whatever other things too. We have so much of daylight, our people don't want to start early. What time do you start teaching in your college? 8 o'clock or 9?
In our Andhra University, classes start at 9 o'clock.
That's what I'm saying. In some colleges, it's not even 9. It's JNTU here, Hyderabad, 9:40 is the first lecture. 9:40, 9:50. I think many private colleges also start at 10 because the buses have to come from somewhere.
So that is it. So only in IITs and NIT, in some NITs, classes are starting at 8.
100% residential.
Sir, 30 participants are there. Maybe we can start and the rest will join, sir.
Sure, it's up to you. 5 minutes waited.
Oh, sir.
No problem. Anytime.
Okay, sir.
be subjected to very, very large lateral forces. And once you have a large lateral force at the top, you will end up getting a large moment also at the base. So many times it's a very challenging task because the gravity load is much smaller, very, very the weight of these lateral forces is not. And once you have a large compared lateral force at the lateral force, and you will end up getting a large moment also at the base. So many times it's a very whole challenging task because the gravity load is much smaller, because the weight of these lateral forces is not. And once you have a large compared lateral force and lateral force, and you end up getting a large moment also that we are going into. So many times it's a very renewable challenging task because they are building the gravity load is much smaller, because the weight of these lateral forces is not. And once you have a large compared lateral force and lateral force, and you end up getting a large moment also that we are going into. So many times it's a very renewable challenging task because they are building the gravity load is much smaller, because the weight of these lateral forces and the water. Once you have a large compared lateral force and lateral force, and you end up getting a large moment also at the moment that you get going into. So many times it's a very challenging task because they are building the gravity load is much smaller, because the weight of these lateral forces 2 meganewton at a height of something like 90 to 100, 120 meters. So imagine the moment, it will become something like 220 meganewton meters, and at this top of the sea, and if you look at the bottom of the sea, you have to add another 40, 50 meters too. And these transmission type foundations on the ground, some of them use inverted T type, but generally they are not adequate. So we end up going for pile foundations too. All these footings are supported by piles, you will end up getting this. So this gives you the kind of picture that you have. One is the horizontal axis wind turbine, the other is the vertical one. The vertical one instantly gives you a lot of torque also. So you'll end up, we are not going to look at that part of it, but we may have to design, if you have a vertical axis wind turbine, for torques too. Now all these piles, the kind of stage that it has gone up, you can see the height, how it is increasing, and you have very, very tall wind turbines. I believe now they're about 120 meters high from the sea level, and this gives you the kind of challenge. Okay. All these, so other interesting thing is, these wind turbines are subjected to cyclic loading because the wind is not there all the time, or the wave action is not there all the time. So you will getting a cyclic load effect, in which case the stiffness of pile soil interaction, it starts degrading. As you can see here, initially it could be some value. If you go for number of cycles, you'll end up getting what is called the pseudostatic one, and which need large lateral displacements. If you look at the bottom one, you can see a large lateral displacement, after which it may behave pseudostatically. Now, whatever we have seen till now are structural piles which take load from the gravity, wind, etc. But I want you to look at a couple of pictures at the bottom where a retaining wall is supported by piles, in which case it is the soil which is lateral force which will transmit it to the piles. So it is not a structural load in the true sense. Similarly, if you have a deep excavation, we go for sheet piles, diaphragm walls, secant piles, etc. Here again, because the soil has a tendency to move once you start excavating and removing the soil in the excavation, then you will have forces coming onto the pile because of the soil movement. So here it's excavation support, and the pile loading is due to soil movement. These are some of those examples of pile walls for retention. And this is what you would see in most of the cities where people are going for 3, 5 basements in a tall structure. Imagine 5 basements means 5 into 3.5 or 4, 20-meter excavation. There is one deep excavation for metro, wherein it was something like 40 meters. And you had to provide this either diaphragm walls, secant pile walls, or contiguous pile walls, and they're all subjected to the soil pressure. So you had to take care of that. Then we are also using this is an example from Hong Kong, but we have done that in a couple of places in the Himalayas to support the slope, which is likely to move and fail. One of the ideas is why don't we have pile support to the slopes? And if you have a tall structure or residential area next to a slope, you want to make sure the slope failure doesn't occur. And one of the best things would be this. Way back in 1970s, one of the dams in Himachal Pradesh, it had to be stabilized because of a shear zone they found out during construction. And there was no way to change the design of the dam. So we had to provide deep well foundations to take care of the lateral forces in the slope or the shear zone. So this is how they work. When you have piles for a slope or any of these structures, the failure surface, as you can see here, is intercepted by these piles. So the force in the pile gives you the stabilizing force. Most of the slopes are generally stabilized with the piles at the toe, and this is where you can have even large diameter board concrete piles. Off late, of course, we are able to now use some geosynthetic gabion walls to stabilize the slope, but this is a very common one in case you find that the surface support is not good enough. So in an embankment also, below a bridge deck, you have to take care of it because the abutment to be subjected to large forces. So they have piles below the embankment to take care of the lateral forces. So this is how, as I told you, the stability of the factor of safety against failure can be increased by the pile. The soil above the failure surface is trying to push the pile to the left, and the pile below the active zone is offering resistance. So lateral force and moment, resisting force and moment are the ones that give rise to improvement in factor safety. So this is a very challenging one because the calculation of load in the active zone is much more difficult because it's not a structural load, but it is a load due to movement, and we don't know how much to do that. We're also using piles to resist ground movements associated with tunneling. Whenever we have this metro tunnel, you may have obviously both vertical and lateral movements towards the excavation. No amount of care will prevent lateral these movements because even with your tunnel boring machines, some movement does occur. And if you have a structure near the ground surface, it would be obviously subjected to these movements. So one of the best ways would be to provide reinforcement. And that means you provide piles so that the building is not affected by to the same extent. You may not be able to prevent it 100%, but you have to take care of it. Just to give you an example, in Singapore, one of the tunnels, if there is any building near a board, the maximum moment they allow was 1 to 2 millimeters. That's all that building is allowed to deform. And the same thing is happening even here. Essentially a project for a metro pillar. Next to it, they want to do an excavation, and we had to provide a very, very complex support system, including micropiles, anchors, nailing, etc., so that the maximum moment a metro pillar can undergo is hardly 1 to 2 millimeters. If it is more than that, the track gets distorted and the trains get jammed or derailed. So that's the problem. In addition to all this, we have the seismic forces, and they're all generated in the ground, which means the building is subjected to lateral forces because of the seismic action. The seismic wave moves up from the bottom up towards the building, and you will have a lot of attenuation, the magnification of the one, particularly if you have soft soils. And as you can see, the north particularly, where we have zone 4 and 5, the uh, fawn-colored area is zone 5, starting from Kutch here, Jammu, Kashmir, Himachal, Uttarakhand, North Bihar, Nepal, etc. And most of the Indo-Gangetic LUM is in zone 4, so there you had to design again for seismic forces of very large intensity. Fortunately, if you are working in the south or central India, it's only zone 3. So it's not as bad, but you still have to design for these accelerations, which are of the order of, I think, 0.12 to 0.16 for zone 3 and 0.08 to zero point 0.1 in zone 2. You have to take care of these forces. So when I'm looking at piles which are subjected to lateral load, the first classification we look at is the length. If it is depending on the length, we classify it short, intermediate, or long. In terms of restraint. Restraint means, is the top allowed to move freely? Is it allowed to rotate freely? Similarly, is the bottom embedded in hard rock, or is it again free, fixed, or hinged? So all these boundary conditions are important because lateral loaded pile behaves like a beam, whereas axial loaded pile looks like is modeled as a column, which means we have less of a problem of fixity. Unless it's extremely long, we don't expect it to buckle at all. So it's purely compression for axial loaded piles, both in compression or pull load. Axial loaded pile, you had to worry about all these boundary conditions because of the beam action. One of the simplest ways in which we classify, very simple one, you define a parameter called beta, which is nothing but coefficient of subgrade reaction KH times the diameter of the pile by 4 EP IP. EP is the modulus of elasticity of the pile material, IP is the moment of inertia, and so we take this product to the power of 1/4, and that beta. Beta has units of 1 by L. So if you have beta times L less than 0.5, the pile is treated as a short rigid one, which means it will just rotate, will not deflect like a beam. If beta L is greater than 1.5, then it becomes infinitely long, which means it's fixed at the bottom, only the top would be deflecting. Intermediate one is where you have the deflections or deformations right from top to bottom. Now, this classification depends on different methodologies we have. You may find different ones too. Now, in terms of restraint, the head can be free, which is what you have in case of transmission towers or single pole ones. Whereas most piles we have, which we embed in a pile cap, the head is prevented from rotating, but it's allowed to translate. Please remember, it should be, when I say fixed, it's only fixed in the sense of rotation and not in translation. So it can move laterally, but the shape is exactly the vertical one at that place. Similarly, at the base or the tip of the pile, if you do it, it's a floating pile. I drive into, let's say, I have an Indo-Gangetic stratum where I have no hard rock. So even if I have 20, 30 meter long pile, the bottom is free to deflect or rotate. That means free. Suppose I end up getting a very strong hard stratum, and I drive the pile hardly into 1, 2, maybe 2, 3 diameters, then prevented from movement, but it is allowed to rotate, which means, in our beam theory, we treat it as a hinge connection or pin connection. Now, if I socket the pile into hard rock, maybe something like 5 diameters or more, then the pile tip is not allowed to rotate and displace. So that is true fixity with respect to rotation and displacement. So because of the beam action, these are all necessary for you to consider. Now let's look at the behavior of the piles, how they do in order to calculate the ultimate capacity. We have the classic theory of Brahms, which I would like you to caution is not valid anymore, but sadly just now Professor Reddy said use IS code, I would rather ask you to use your judgment whether it is true or not. I want you to know that Brahms came with this theory in 1964 ASCE. His experience at that time was based purely in Sweden, and where they have extremely soft soils in some of the areas. So on the left, we have a free short pile. Because it's a short pile, it acts like a rigid one, so it will rotate about a point of rotation at a depth h. So the pile will rotate to the right because of the horizontal force at the top. Below the point of rotation, the pile will move to the left. So if I look at the pressure distribution, you will have, because the pile is moving to the right, you will have reaction from the soil from the right onto the pile. From point B to C, B is the point of rotation, you will see that the soil reaction is from the left onto the pile. Now, this could be how the momentum in the pressure distribution is. He simplifies it as kind of linear value, and then it's very easy for us to calculate the forces and moments, etc. The only thing is actually it will be nonlinear with a finite resistance at the top too. For some reason, Brahms said, let's neglect the top 1.5 meter, 1.5 times d. As you can see, in these two cases, the soil reaction in the top is neglected. I want you to realize we don't keep a pile at the ground level. Most of our piles are 3-4 meters deep, etc. So when you are calculating the lateral resistance, please don't ignore that 1.5D. And then he said the movement is so large that the full resistance of 9 times Cu into D is 9 times Cu is the maximum lateral resistance. Like if you have a shallow foundation, for a steep foundation, bearing capacity is 5.14 into Cu for coarser soil. For a subtler footing, it's 1.2 into 5.14, it's about 6.14 times Cu. Because pile is a three-dimensional one, it's not strict, so you will get maximum. Actually, it varies from 8 to 12. In our design practice, we adopt something like 9 times Cu as the maximum bearing stress that you can get from the soil. As I said, above the point of rotation, the reaction is from the right, so you have the strip load coming here, or the uniform load, and below the point of rotation, the reaction is coming from here. So it's very easy. Once you work out the equations of equilibrium, you can calculate the maximum load. That in all the design charts, we look at the point eccentricity also. The horizontal load need not be at the ground level. Often it is much above the ground level, so you can include that. And now if you look at the bending moment diagram, because of this loading, the force here is H, the reaction is coming from here, the max bending moment increases with depth, reaches a maximum at some depth, and then becomes zero because this is a free pile at the bottom, there is no fixity, so it is zero. So this is what happens for a short pile. Now imagine if the pile becomes longer, this is a longer pile, and this bending moment keeps on increasing as you increase the length of the pile, and then you suddenly say, no, the pile cannot take any more, it reaches its plastic stage and it forms a plastic hinge. If that happens, the mechanism is very different now. In the long pile, we treat the hinge here at some depth, and the pile rotates like a free one here because it becomes a short one. So you have this kind of pressure, and below is the other one. You have to calculate now based on the plastic, what is it? Maximum bending moment or your moment. And this is how we do it in case of coarser soils. Okay, that is for free head. Now I want you to look at the fixed head one. So here we have the pile embedded in a pile cap, and the load is applied here. Because it's a short pile, it rotates like a rigid one, which means with the H, it simply translates to the right. Now, if it is an intermediate pile, or you have the moment so high because fixed end moment, it can form a hinge here and it rotates again as before. If you have very long pile, you will end up getting a hinge at the pile cap and another hinge somewhere in between. So this is what happens for short, intermediate, and long piles in coastal soil. In each of these cases, I want you to look at the kinematics or mechanics. This is the soil reaction, and you can see the bending moment too. Because of the fixed T and all the load is here, the maximum bending moment occurs at the top. So the first hinge can occur, formulate here at this place as you keep on increasing the length of the pile. So for very short piles with no hinge, we use this kind of mechanism. With intermediate piles, possibly one hinge here and then rigid below. So this is the kind of soil pressure distribution. These are all according to Brom's theory, which has been later modified by several people. And I'll probably end up my presentation with some work we did here on the considering the movement. The main reason is in case of piles, the limiting value is the displacement. And nobody would like to design lateral loaded pile for more than 5 millimeter displacement. A very long pile extending from the intermediate one, you have one hinge at the pile cap, and then the bending moment here becomes very large too. As you can see, it is the negative moment here, and it's the positive moment. So different types of moment. So you still end up getting a plastic hinge because of which the pile may behave very differently. So these mechanisms are very important, and you have to work out based on the relative length of the pile. In case of cohesionless soil, obviously the reactions will be very different. As you can see here, the vertical stress at the top is zero. All the resistance you get in case of granular soils is normal stress, which is gamma into Z into Ka or Kp. What we are looking here is, again, I want you to see, because the pile is moving towards the soil, obviously it will be passive pressure. If it is a wall, I would have said the pressure is equal to gamma Z into Kp. Because of the three-dimensional effect, the pile pushes the soil on both sides. It's not a plane strain problem. We end up getting a factor 3, which is what Roms has recommended. Nowadays, people even go for 4, 5 as the, after we realize it can be slightly more too. So the reaction from the soil is not constant with depth, it increases with depth. So we have to look at and in this case, we find that it's easy to, if the point of rotation is slightly above the ground, we shift it to the bottom and then extend the reactions, the free body diagram and calculate the thing. So as any moment again increases from the top and becomes zero at the bottom. So if I increase the length of the pile, as the one you see on the bottom here, the hinge can form here, which means the soil reaction increases, then decreases and becomes go to the other side. So based on that is the moment, and we use these for our calculation. This is a free head pile in cohesionless soil. If I have a fixed head pile, you can see very similar mechanisms. You have simple translation at the top. So it's very easy to calculate the reaction in this case, linear increase, and H is equal to area of this triangle. Please note that the lateral pressure is 3 times Kp times gamma into Z or gamma into L. And the maximum moment is, negative moment is here. Then if you increase it, you will end up getting, this is the first field moment. And if you have very long pile, you will end up getting 2 hinges, and we still do the same analysis. The analysis is very simple, but the mechanism is very important. So you have to be very careful in these two. If you have a socketed pile, I told you, if the socket is short, then you will end up getting point of rotation. It's fixed, but it's allowed to rotate. And in the rock, you'll end up getting very large lateral forces, and we integrate for that. And when you have a very large, long length, you can get a hinge here, and then you get this mechanism. Please note that here the socketing is very similar to the depth of penetration into the ground. So based on these, we have all these design charts which are available in our code also, but all of them are based on Brom's theory. So I want you to look at the chart depending on the amendment, which is nothing but L by D ratio, against which you have ultimate lateral resistance in coarse soil, P by Cu into D square. Cu is the undrained strength, and D is the diameter. So you have a non-dimensional ultimate lateral resistance. It's a function of eccentricity, so E by D. As you increase eccentricity, obviously the moment increases, the capacity decreases. So you will realize that P by CUD square can probably as high as 60 for maybe L by D of 14, 15, etc. It can reduce by a factor of 2 to 16 once you have a large eccentricity. It's not a big thing in terms of eccentricity because diameter of the pile is 0.6 to 1 meter. So if you have a tall structure or a single pole which is going up to 16 meters, 15, you get E by D there. So you can calculate using this. If you have a fixed head pile inside here, then the effect of eccentricity is not there. So simply you get as a function of L by D, and you get fairly large restraint. So you'll end up getting P by Cu into D of the order of 50, even for L by D equal to 8. Then you may say, what happens after that? Then suddenly you will get hinge too. So these are the kind of chart that we have. We can also put in terms of the yield moment here. This is MP, restraint 1 with 1 hinge. Yield moment by Cu into D cube we calculate. If you know the section of the pile material, you can calculate the yield moment, which is your yield stress into the moment of inertia function. Then you will get M yield moment, and Cu by D cube will give you the non-dimensional parameter. So it becomes obviously little less than a short pile one. So these are the charts that you have for piles in clay. These are for long piles. You can see here, and very similar ones too. And what I would like you to do here is on the right side, we have long piles. This is yield moment by Cu into D cube. It can vary from 1 to let's say 100 or 1000. And H by Cu into D square is now restricted to much smaller value. You can calculate for different eccentricities, and these are all charts available in our code. You can easily use them for your design. For cohesionless soil, analysis is very similar, but only thing is the quantities are very different. You see again here as a function of L by D and a function of E by L. These are for free head piles. And here you have the lateral force, the horizontal force is normalized by Kp into gamma into dq. Please remember, gamma is unit weight of soil. So let's say it is grams per cc. So you need to multiply by dq to end up getting a force, and you normalize it. So you calculate, Kp is a function of angular shearing resistance. 1 plus sine phi by 1 minus sine phi is a very simple expression. And here is our pile with eccentricity E. In this case, for E by L is equal to 0. That means at ground level, the normalized lateral force is close to 200. But once you have eccentricity of the order of 3, it reduces to even less than maybe 45, 50, something like that. And if you have, rotation here at the top because of fixed T with 1 hinge, here are the design chart that we have for coarse soil. You'll find them in the book or any of the codes you will find. Now, in case of long piles, again, you have the ultimate yield moment here normalized with Kp gamma into D4. Because please note that this is the yield moment. So I had to have Kp gamma D4 and your normalized lateral force, and you can see a curve for restrained head and the free head values for different eccentricities. And this is long, weak pile, which means you have double hinges and you have a different chart for this based on how you analyze, which means you had to use L by D, you had to use yield moment of the pile, and you had to know the eccentricity of the load, and based on that you get these things. What we found is that many times the lateral capacity is not enough. People say, what should we do in order to increase the lateral capacity? One way is to increase the number of piles, but that is a very, very expensive thing. So what often we try to do would be, if I can provide additional support through sand or gravel blanket here, so that this top is restrained. Or for the pile, it's like your vein, if you can attach blades. Doing this also by increasing the plan area, so when it rotates or deflects, you have more area resisting. A very common one would be what we have been recommending also, is to have a collar. Recently we had a problem where the capacity was very less in a particular port structure. We said, why don't you increase the diameter of the pile in the top, so that will give you more resistance. The pity is that in case of piles, it is only the top that controls. You may have a very stiff soil at the bottom, but its contribution to the capacity or reducing displacements is much less, because pile is a cantilever and cantilevers have large deflections, and that's the problem. You can also have, excavate around and pour concrete plug here. Some people suggested, why don't you provide a beam? But this is possible only if you, in case of a port structure where the direction of the lateral force is fixed. Okay, then you can say, I'll provide a beam to stop it from moving. Similar to that, we have a short pier to the next to the right, getting the lateral force too. So these piers, as you can see, can be provided in this fashion. So these are alternate ways in which you can improve the capacity. Now again, as Professor Reddy has told you, we want to analyze for the working load condition. Ultimate load may be say 25, 30 tons, but actually we design only for 5 to 10 tons. But then even then we need to work out in terms of displacements, because the displacement control in all our design in geotechnical engineering, while the ultimate load and safe load will take care of the stability, the serviceability is very important. So when you have this pile subjected to load, at working load, you will find that the maximum deflection is where the load is acting. Soil reaction curve is something like this, but you will see that the maximum deflection occurs here. And how do we do the analysis? As I said, pile is a beam. We had to find out its response. One of the simplest models we have is what they call as a Winkler, who gave his model way back in 1885 or so. He says, replace the soil with a set of springs. And the spring coefficient is called the coefficient of substrate reaction. So what we say, let's put the pile and then the springs which keep along the length. And original Winkler model is all the springs are unconnected, which is again a limitation. This is slider here, which means at the top, the displacement is so high, the soil will start shearing. So you will have large displacements, and then the limiting shear stress is mobilized, or normal stress. So those are being reflected here in this. And as I showed you earlier, the reaction soil pressure would be something like this, which we had to determine that. Now, when I do this, I do a simple load test. Let's say a load test or a lateral load test, wherein I have deflection and the soil resistance, P Y curve, as they call it. P is the soil resistance, normal force or normal stress on the pile, Y is the deflection. When you do a simple lateral load plate, laterally loaded plate load test, you may get a curve of this kind. The problem with this is that the initial portion is very steep, so you will get tangent modulus high, but actual displacements are large, so you may have to use a secant modulus value. So please remember, the modulus of subrate reaction is not exactly a constant. You have to look at in terms of displacement. Okay. Now, when you come to sands, obviously at the top there is no restraint, so the modulus of subrate reaction or coefficient of subrate reaction is 0. It increases with depth. It can increase in any fashion, non-linearly, but most of the time we assume a linear increase, and which means the modulus of deformation or subrate reaction increases linearly with depth, and we use this parameter NH, which is the rate of increase of modulus with. So we had to analyze this, and this is what I want you to realize. As I said, the pile is subjected to vertical force, moment, and horizontal force. At the top, the deflections are very large. So I have PY curve, but the displacement is so high. The secant modulus now, I had to look at the slope here, and so I get E pi y or ky 1. If I go to the next level, the deflection is smaller, so the secant modulus is more because the curve, this is steeper than the one here. Two things can happen. Both the capacity increases, lateral capacity, because at greater depth it can be more, and the stiffness is more too. So the non-homogeneity is very important in all the pile analysis. And if you go deeper, you can see the PY curve is much steeper and you get larger capacity. So this spring constant is not honestly unique value. It depends on the depth. It depends on the soil at different depths too. So we have a lot of choice that you have to make in terms of choosing these. So I picked up some of these correlations which are available from literature. So if you do a simple plate load test, I get the 300 millimeter plate, right? So I can get the displacement, and if I want to get the coefficient of subrate reaction for horizontal condition, this is how they recommend it. But if I do a simple triaxial test and I get E50 from the stress strain curve, I convert that into KH. It's 1.67 E50 by D. Please note that the units of KH are force per length cube. It is coefficient subrate reaction is stress by displacement, so it's force by length cube. So now, if you can do this in terms of deformation, if you have undrained strength, people recommend KH is around 80 to 320 times Cu by D. About 100, 120. Okay. Now, again, people have recommended in terms of the modulus of elasticity 0.92, and people said it should also be a function of the pile stiffness. So here is another equation I could get where the x1, the parameter you see here, multiplying the modulus of deformation by D, this parameter is a function of the relative stiffness. This is based on basics theory of bending of beams on continuum. That's how you do that. These are the ones I found in our code too. If you look at the values of plate load test from square plates on over-consolidated clay, if you have very stiff, very stiff and hard stratum, undrained strengths are the order of 0.5 to 1 tons per meter foot square, 1 to 2 and 2 tons per foot square. Range of this case value is 50 to 100, so they propose 75, starting based on Terzaghi. Very stiff soil is about 100, 200, and very hard soil is around 300. These are the values recommended by Terzaghi way back in 1955. Again, I have picked up some of the values of the coefficient NH, which is the rate at which it increases with depth. In the case of soft, normally consolidated clay, Rees and Matlock, who did a lot of work, recommend NH to be 0.6 to 12.7. Please note that these are all in the FPI unit, foot-pound second one, which means the units are not what we are talking in terms of, say, kilonewton per centimeters cube or so. You have to convert them. Normally considered organic clays, I don't think we have, but let's see some of the wind-blown deposit. Both gives you a value of 29 to 40. The NH values are given again by both the relative density of the soil. So you can say if you have sand above the water table, NH can be increasing from something like 10 for loose, relative density of 30, it can go to 75. Relative density, very dense soil around 80, but below the water table, the values become maybe something like half to 1/3. So how do you estimate them? We use a simple kinematics, simple rotation or beam. So here for this deformation conditions, we have a slightly different criterion for different types of piles too. For a free head pile, if beta 2.5, then you treat it as a short one, and beta, I think it should be 1.5, sorry. For a long pile, it's 2.5. So if beta is less than 1.5, it is a simple rigid pile, and then you can calculate the deflection and rotation very easily. So the maximum deflection is equal to 4 times h into 1.1 plus 1.5 E by L, E is eccentricity, divided by KH into D into L. Please remember this KH is the most important parameter here. A structural designer will tell you what is H, what is E. As a geotechnical engineer, you decide on the length and diameter, but the most important parameter is what is KH. Should I take KH at the top, somewhere below, or along the length, but use judgment. And that makes a big difference in all your predictions too. Okay, so that's how we do that. And beta here, in this case, as I showed earlier, is equal to KD by 4EI to the power of 1/4. EI is the pile stiffness, K is the coefficient of subgrade reaction. Basically, it's modulus of grade reaction into diameter, with the diameter of the pile, length of the pile. So, and in this case, if you have a fixed head pile, we have very similar criterion. Beta less than 1.5 is short, beta greater than 1.5 is long pile, and the displacement is very easy to find out here. Because it's a lateral displacement, all the reaction is taken care here. H by KH into D into L is our displacement for short pile. Infinitely long pile means basically it's fixed at the bottom and you have very simple expression H into beta by KH into D. It is intermediate long piles which are more challenging. So these are the ones where you have beta between, let's say, 1.5 to 2.53. You can see initially they're all constant because they're rigid pile. And then once you have the large one, it becomes redundant to look at it. So 1.5 to about 2.53, you will see that it's a function of beta L. So here we expect the coefficient is given here. The coefficient of displacement is a function of eccentricity and the dimensionless length beta L. We defined beta L just now, it's the same value. So the more eccentric the load acting above the ground level, the large displacement. So please note that it's very, very significant in terms of displacement. So even a short pile, beta L is equal to 2, you will have this coefficient is around maybe 8 to 9, 10. Whereas if the pile is axle load is very small, then it's much less. So this is how, these are for free head piles, all this goes, and this is for a restrained head pile, how it varies. Once you put it in a cap and at ground level, no restraint, no eccentricity, so you'll have much smaller displacements. These are the charts for the sands, where you have, now instead of beta, we have what's called a parameter called eta, which is NH, rate of increase of modulus of subgreen reaction with depth divided by EI and to the power of 1/5. And so you have dimension length is eta into L. And the dimension, the coefficient here is given here. So I can, once I get the coefficient, I can calculate the displacement. So here are the curves for free head pile at different eccentricities, and this is for the restrained head pile. So we use this chart to predict based on the Winkler hypothesis. So basically, this is what we normally try to look at it. And I would like you to look in terms of critical length. You can find out how much is the critical length from this simple expression. And for a homogeneous soil, we can use the simple expressions here for both lateral load and moment. I tell you only in terms of eccentricity. But if you want to separate out the effect of lateral force and the moment, this is one simple way of trying to do that. Same Winkler model here, but the expression now you can see is in terms of LC, the critical length. And if length is more than the critical length, then it becomes significant and use this value. Okay, so you have the contribution from the horizontal force and the contribution from the moment from this expression, and the rotation also is very similar too. So we can use the calculations to do that. Okay, these are the expressions for non-homogeneous soil, which means sands, where the coefficient K is a linear function of depth. Now, in this case, the critical length LC is defined in terms of the NH, you can see here, to the power of 1/5, and the displacements are lateral force and the moment. So this we use in our expression. However, what we found that is this Winkler model is not exactly good because soil is treated as a set of springs. Ulas way back in 70s has developed, which is now being used in many design problems, and we use in all our modern design checks too. The soil is treated as a continuum, which means you have, it's a modulus of elasticity. The springs are in a way connected. I didn't want to go into the design analysis of this, is fairly complicated, but the best part I would like you to look at is, in this case, the deflection is a function of modulus of deformation of the soil, length of the pile. This is the influence coefficient for displacement due to the force, and this is for the displacement of the moment due to moment, another influence coefficient. And he is also given in terms of factor of safety with respect to ultimate load. So you are looking at the elastoplastic deformations. And rotation is given here, theta, in terms of this, but everything depends on this coefficient Kr, which is nothing but a relative pile flexibility. To me, this is a very, very important parameter where Kr is equal to EP by Es into L4. E is the modulus of elasticity of pile. IP is the moment of inertia of the pile material. Es is the modulus of deformation of the soil, which is what you can normally get, L4, L to the power of 4. And these are the parameters you have. The influence coefficient due to horizontal load, influence coefficient due to moment. Similarly, influence coefficient for rotation due to horizontal load, and influence coefficient due to moment, and F rho or F, that factor is with respect to yield displacement factor in the, as long as the soil doesn't yield and constantly. So we have several charts. This is what I would like you to adopt in all your design. So the free head floating pile, if I can calculate Kr, as I showed you, Kr is a very simple term. EP IP by Es into L4. You get that. Once you have Kr, I can calculate I rho h, and once you have I rho h, I substitute here. Similarly, I can do I rho m. Here is our I rho m, and you can get that. And here is I theta m. This is the influence coefficient for rotation due to moment. I want you to see here, once you have a very high value of Kr, more than 10 to the power of -1, it becomes rigid and the coefficient becomes constant. And for intermediate or highly flexible one, the IROH keeps increasing. And below 10 to the power of minus 6, highly flexible, you can't have any design of pile foundation. The charts for IROH, IRO-M, that means influence coefficient for displacement due to movement, and using your compatibility Waterworth one, it's the same thing as influence coefficient for rotation due to horizontal force. And this is influence coefficient for rotation due to movement. For pre-head pile, for a fixed head pile, we have very similar values too. You can see IRO, F, there's no rotation here, and you have much smaller deflections, obviously, and the coefficient is very easy to calculate too. So, as a and L by D. Usually our L by Ds are in the range of 25 to 50, so we can pick up any value in this range, or you can interpolate that too. Now, when E is increasing linearly with depth, instead of Kr, we have Kn, which is EP IP by NH, which is the rate at which the modulus is increasing with depth, into L to the power of 5. So we have solutions for these two. So I would like you to forget Winkler model. You may do it at the first iteration, but if you want to do a final design, go for this continuum approach. And we have influence coefficient due to horizontal force. This is influence coefficient for horizontal displacement due to moment, or influence coefficient for rotation due to horizontal force. And this is influence coefficient for rotation based on moment too. All of them are functions of Kn, which is defined here as EP IP by NH5. If you have socketed pile, that means you have driven the pile into hard rock, hardly 1 or 2 diameters, then you can end up two conditions. If the socketing is very small, you have pin condition. If the socketing is very large, you have fixed condition. And then you see, initially, if it is, flexible pile, it doesn't make a difference because the behavior of the pile is only in the top. But once you have a relatively stiff pile, socketing at the bottom makes a difference, which is, of course, very unusual because most of the time, we are only interested in the relative flexible piles. Highly fixed steel, nobody is able to drive, say, very large depths into hard rock. That means you cannot get socketing where your pile tip is also fixed, no lateral displacement and rotation. So these are the design charts you will get from many standard books like Poulos and Davis, etc. We can design them. Other one I want to now talk about would be, what do we do in case of buildings on piles due to earthquake? This is a very challenging job because once you have a building in a seismic area, somehow our conventional belief is that providing piles will help. But please remember, if the soil here is a fine saturated sand, it may get liquefied. So the damages can be very, very significant, even though you may have piles. There could be two reasons. One is due to inertial force on the building, and the second would be the kinematics of the ground itself. And if the soil here at the shallow depths gets liquefied, which is what happens most often, obviously the lateral support is gone. Our coefficient of subreaction becomes 0, the modulus of deformation becomes 0, and the whole pile system may not function at all. So the kind of different failures possible would be something like this. Please remember, these are all the inertial effects. The effect of earthquake on the building would be to cause large displacements, large moments. So, and you can end up getting the pile buckling, it can have shear failure, bending, or even dynamic amplification is so high, the large deflections may take place too. So in general, if you have to design a tall structure in a seismic area, you have to be very, very careful. No matter how much you provide, the problem would be liquefaction. And if you have a soil which is likely to get liquefied, liquefied, what happens? There hardly any resistance here. So if I look at the factor of safety, it is less than 1. I have fine sand, clay sand, or this is poorly graded sand, so there hardly any resistance to the piles. And you know that the resistance only in this region is important for lateral forces. So even though you have provided below, this is a non-liquefiable layer, but this is what happens most of the time. If you're designing in the of India, we did few projects for Guwahati, and this is what happened. And you will end up getting very low factors of safety. And when we do the liquefaction analysis, I'm sorry, before that, look at the SPTN. N values are all less than 10 to a depth of something like maybe 8 to 10 meters. So obviously this soil is going to get liquefied. So this is a clay sand and fine grained sand. The factor of safety is less than 1, which means this area is going to be liquefied. So once you have liquefaction, there hardly any resistance to the soil, and you will end up getting the whole pile within the liquefied zone as acting like a cantilever. There hardly any resistance. So you may have a very long pile, but the pile is now fixed only in the non-liquefied zone at the bottom. So you'll end up getting large deflections, and it's very, very difficult to design them for these earthquake conditions. So it could be also both inertial and cyclic. The building is shaking, so it gives you inertial forces. You have the kinematics, the lateral spread, the soil itself is moving, and you will see the pile moving with the soil or relative to the soil. So this is the problem we'll have to design for. So in order to do that, what people recommend is you try to calculate what is called as the liquefaction potential index, which is a function of Fz, which is a function of your factor of safety against liquefaction. And then based on that, and W is of course the displacement, or the way in which the displacement varies with it. So it increases from 10 minus 0.5 Z, and you calculate LPI. And if LPI is very small, let's say 0 to 2, no problem. But liquefaction potential is high, you'll end up getting very serious problem. This is the how you reduce the modulus of subgrade reaction. So if it is more than 10, you can say that if liquefaction potential is greater than 5 or 10, you can see both are on log scale. Please note that even if it is 10, the factor reduces to 1/10. So what you thought n is your SQ, and these are all verified with experimental data. So we had to be very, very careful in terms of designing pile foundations to take care of seismic load. You have very small subgrade reaction. It can reduce even something like 0.05, 0.02, which is a very small value. It doesn't matter even if n value is 14 to 20, it reduces, which means normally we say n less than 10 is where the seismic liquefaction is very important. But even n is equal to 14 has given us the values. These are the kind of predictions that we get now, which are validated with experimental data. So what we did was in one of the projects, they had both cast in situ piles for a seismic area. I think this is probably where we talked in terms of Delhi Metro. And we also said, can I prevent liquefaction? By burning stone columns or gravel drains. And we were trying to convince them that instead of providing both cast in situ piles, why not use stone columns? It's also useful in terms of carbon footprint. I don't know how many of you realize that when you use concrete and steel, the amount of carbon dioxide generated is phenomenal. 1 ton of cement to manufacture generates 1.5 tons of carbon dioxide. 1 ton of steel generates 2 tons of carbon dioxide. So if I can do a sustainable design, I would always recommend you to go for that. And we were recommending going for these piles to take care of the lateral forces for a metro condition, even for Delhi. Please note that It's not a highly seismic one, zone 3. Maybe they're designed for zone 4 as an extra precaution. Whereas if I use stone columns, I don't use concrete and reinforcement. I use only stone aggregate. So including wastage, the amount of carbon dioxide produced is much smaller. So for a typical project, if you work out the carbon footprint, if you use both cast in situ piles, for each pile, you're generating carbon footprint of 1,249 tons. Whereas if you go for stone columns, it's hardly 161 tons. Even otherwise, I would recommend that we go for some ground treatment so that you prevent liquefaction rather than design for liquefaction. I want you to realize this is how we had to look for it. So liquefaction occurs because the soil is in a loose state. If the sand particles you want to visualize in a loose state, I want you to look at the grains, one sitting on top of other. But during an earthquake, the pore pressure development and particles probably tend to collapse. But if I can densify the sand so that I get a dense state, which means the void spaces are small, I can easily achieve a dense state without any problem, and I can also have no liquefaction and prevent liquefaction. How do we do that? We can do in terms of applying energy at the ground level. You can tamp it with a heavy weight, or you provide a vibrator, vibratory roller, vibratory plate. This is good for in the top 5-7 meters. A heavy tamping is good for 5 to 10 meters, whereas this vibratory plate is only for 1 or 2 meters. But if you want to densify in the top 5, 10, 15 meters, you go for these compaction piles, what the Japanese call as the sand piles, or we have vibrocompaction. Very deep you can use for these explosives. I'm not recommending that for our case. So when I look at vibrocompaction, we provide this vibrator. It goes to the depth. The vibrator needle goes down, and once it reaches the required depth, the vibration itself densifies the sand, and you get a very high dense granular material, and that becomes a very stiff material which is not liquefied at all. There are only loose sand densify. Loose sands liquefy, and dense sand don't. If necessary, we add a granular material because of the space created due to compaction of the loose sand, and that becomes a very stiff material. I just want to show you what happened. We always try to check whether the improvement occurred or not. So if you look at this particular case, you can see the N values were odd. The tip resistance is very small before treatment with vibrocompaction. And once you vibrocompact it, the tip resistance initially was less than 2. Now it has become more than 5. It's close to 7, 8. And so once you do this, we always check the pre and post treatment of the strata. You are very, very sure that liquefaction can be prevented. So this is how we validate one particular corporate project in Punjab. This is for a building in Noida, in Delhi. And you can see the initial values, and values were 10, 15, etc. But after ground treatment, they all became more than 15, 20, even 30 here. And they wanted a verification in terms of plate load test. If you do that, even under 30, 40 tons, you hardly get 5 millimeter displacement or settlement, which means the required densification occurred. And this was, of course, the design chart they expected, that how much improvement. It you get much more than that. So ground treatment or engineering of ground is very important. This is in UP, Western UP, another packaging unit, where they had initially very low values in the sandy silt or silty sand. And once you do vibrocompaction, the values have all gone above 20 to 30, which means you can be sure that there will be no liquefaction here. Now I just want to just briefly go how you can design the whole thing based on the displacement. In terms of piles, we have to be very careful. Professor Padmavati is a JNTU. She did all this work, and we were trying to analyze based on these nonlinear response of the pile-soil interaction, and we combined all these analysis in our design for various cases, looking at the whole response, not simple linear elastic. We also did for both coarser soils and coarserless soil, short piles and long piles. We do the usual mechanism, and we were trying to compare our results with what others are doing. So this is how we assume Ks with depth is increasing with depth. The ultimate resistance also is increasing with depth. And we took the values from the Zaghi and other published data. We did the analysis for various conditions, relative stiffness factor, very eccentricity. What you find is here is the lateral normalized force against displacement. So once you have this for E by L is equal to 0, and we are finding out the load displacement relation. And in case you find that it's not reaching ultimate value, we try to find out ultimate using the Shin's method. And this is how the point of rotation varies with depth for different values of mu. But I would like you to come back to this is what I want to show. The point is this is what the Brahms has given, but we found depending on our assumed value of Kp, it can be very different. So please remember the Kp is here when we had to do that too. And we are comparing with the published data, and the code doesn't always help. More eccentric load, it becomes more. So we are trying to compare with the published data, and you find that in some cases pretty good, but in other cases can be very different. This is how it is. It's fairly good, I would say. Let me come to the where we are matching with the values. Yeah, this is how I would like to look at the graph on the right, and what others have predicted and what Dr. Padmavati predicted is very close to what the measured values are in many of the practical situations. So we can do the analysis more rigorously, and we don't ignore the top. We were saying the resistance increases from ground level up to a depth of 3D and then calculate the whole thing. Yeah, this is what again I found out from Ula's book. Brahms is predicting values which are very different from what you get based on kinematics. McDonald in 1999 said don't ignore the top 1.5, and he recommended his design charts too. So these are our predictions which seem to match well. And this is what I would also like to do. We have some experimental data from field K, and this is what these dots are measured values, and this is what Padmavati predicted. And look at what Brahms has predicted. Doesn't match at all. So these are various comparisons. We also did some work for two-laid soil. Those of you who would like to pursue this, it's a good problem to work on. Yeah, this is how we can validate your result. So I just would like to end up saying that it has been a pleasure teaching or giving my share of experience using laterally loaded piles in our design practice. These are some very interesting trees apparently in Poland. How they became like this, nobody knows. But this to me looks like one of our complex problems we deal with. I'd like to end my presentation with my signature, which says, geotech engineering is a science, but it's practice and art. I'd like to thank you for your patient listening, and I'd be very happy to answer any queries you may have. Please, share your concerns on this anytime. Okay? So I look forward to your questions.
Sir, good morning, sir.
Good morning.
Sir, this is
Yeah.
Dr. Rashekar from Andhra University, assistant professor.
Okay. Okay.
My question
Nice.
is, uh, in modeling file using PY curve method,
Mhm.
how to model file using springs, using how many degrees of freedom, sir?
For lateral loaded pile, I have only 1 degree of freedom for static condition. If
Only
you
one,
have
sir?
only 1 degree of freedom, lateral movement and rotation, that's all. I don't have degrees of freedom in terms
Lateral
of,
and
you are talking in terms of
will
vibrations.
not consider 60 degrees of freedom.
I'm looking at only the static and
Not
pseudo-static.
vibration, sir. Dynamic load, sir. Dynamic load.
Yeah, which means it's dynamic. We don't design for dynamic load. Most of the
You
buildings we
don't
design,
need to.
that is beyond, but I didn't cover that part. I haven't done the
Okay.
dynamic analysis of the piles. I have done only for the static load and pseudo-static, how
Cyclic.
to design. That's a very complex problem.
Okay.
If you're designing for dynamic loads under seismic condition, when you're doing spectral analysis or amplification, etc., you're designing the building for multi degrees of freedom. That is very difficult. I haven't done it, and this
One more,
lecture
sir.
doesn't show.
Thank you. One more, sir.
Yeah.
What is the effect of water on file foundation, sir, and the soil around the file in designing a
Water-
PY curve method?
I told you now, if you have soil below the groundwater table, the subgrade modulus decreases, and above the groundwater level, subgrade modulus is higher. That's how we do that. But my suggestion is,
Those values you have to consider.
yeah, below and above you have
Accordingly, you have
different
to
values.
take. Okay.
Honestly, very little. Only the Americans follow that kind of a thing, but most other cases we don't use PY curves at all. Go for continuum analysis. Okay, and then you determine what is the value of modulus, saturated soil or partially saturated soil.
Okay. For each soil condition, you have to take separate soil models. Sir?
That is the thing. Basically, in geotechnical engineering, there is nothing unique about the ground. Each site is different. Within a site, you may have different variabilities too.
Okay. Thank you, sir. It's nice.
You're welcome. Sure.
Yes, sir.
My pleasure.
Yes, thank you. Thank you.
Yeah. Anybody else, please? What is that D by 2 effect? There's no D by 2. Somebody put a question. Experimental results don't have the D by 2 comes from your modeling. Any more? Otherwise, I would like to thank you all for your patient listening.
Sir, sorry to interrupt. Can I ask you?
No, sure.
Sir, so what are the parameters that structural designer has to take care so when he receives a soil report, especially in the earthquake zones and when he's designing for a pile foundations?
First thing I look for is basically the SPT N value, how it varies with depth, the groundwater conditions, and the grain size distribution. Please remember, fine sands under groundwater with SPT N less than 10 are definitely like to liquefy. between n value of 10 and 20, it's moderate risk. If n value is more than 20, it doesn't liquefy at all. So when I'm designing, I look for this, and I gave you the liquefaction potential index as a criterion in one of my slides, and use that as your criterion for calculating whether the soil is likely to get liquefied or not. And if you have LPI, liquefaction potential index, I reduce the modulus of subgrid reaction KH. Accordingly, it can reduce to, half, 1/10, even 1/50th, which means the whole structure, for all you know, may collapse. And that is why if you have a site where it is likely to get liquefied, I would say don't go for lateral loaded pile design, improve the ground, then you put your piles to take care of structural loads for axial load, axial compression, etc. The problem with us is we think the piles will solve the problem even under seismic conditions. They don't. There are several failures, even in Japan, with all the latest technology. If the soil liquefies, there's nothing you can do. Please remember the pile gets its resistance near the top, and the soil at the top, if it liquefies, it's bad luck. So what I would suggest is improve the ground so that liquefaction doesn't occur, and you design. And that is the projects I have shown you, several in the North India, where they had these projects where they didn't want liquefaction. They were improved and then designed. Is that clear?
Thank you, sir. Sir, any particular software you would recommend for a structural design engineer so that he can model and pick out the results accurately?
There's nothing accurate in geotechnical engineering. With all my 6 years experience, I recommend whenever I give a settlement of say 25 millimeters, I say it is in the range of 25 to 40 millimeters. I want you to know, you as a structural engineer, I presume you're a structural engineer. Am I right?
Yes,
So
yes, sir. Yes, sir.
you deal with concrete and steel. Am I right? And you deal with IS 4256 or 456 code.
Yes, sir.
Concrete and steel have precise properties. Whether you buy steel from Tata's, SAIL, wherever it is, the ultimate strength is 425 megapascal. The E value is 210 gigapascal. Am I right for steel?
Yes,
And
sir. Exactly.
for concrete, you say, I want M60, M50, M45, you know the strength. It can vary by maybe 5-10%. Okay, and then based on your strength, you also know the modulus of reinforced concrete, which is probably around 20 to 23 gigapascal. Am I right?
Yes, sir. Yes, sir.
I can't say that for soil. Soil doesn't have a property. It depends on how you test it and what are the conditions in the ground. So you have to use judgment and you get a range. We'll never get, this is my problem with all my structural colleagues for the last 55 years. They cannot visualize that soil is different. It's not an engineering material. It's actually like a human being. Does a human being have a property? He may have height, weight, what color, whatever it is, but can you tell how he behaves or she behaves? The ground also behaves depending on what you do or how we analyze the whole thing. So what I normally say is that use this characteristic and get a range of values. Even for that famous Burj Dubai, that Burj Tower, Burj Khalifa they call it, they said the displacement, they spent huge amount of money, and the pile foundations for in through soft rock and limestone went up to 75 meters. Then they said the displacement can vary from 65 to 100 millimeters or whatever it is. Nobody can precisely predict. And this important structure, maybe there were some 10 different consultants, all of them finally came with a range of predictions. You had to use very sophisticated software. There's no simple one. And very few Indian companies have the software which combines the superstructure with the ground, where all these ground characteristics can be combined. It's very expensive.
Thank you, sir. Thank you, sir.
You're welcome. Okay.
Sir, if there are no questions, I thank you once again
Yeah.
for
Welcome.
sparing your time and giving a detailed lecture on lateral load piles. You have covered the issues related to analysis and design of piles with free head and fixed head conditions in different soil conditions. And importantly, you have also explained how to account for reduction. Thank you very much.
Thank you. Hope to see you all on Friday. And that's going to be a very interesting one. I think, Karthikeyan, you can get my email, madhavmr@gmail.com. Somebody wanted, Professor Reddy,
Sir.
you can share my
Yes,
email and number, okay?
sir.
madhavmr@gmail.com, right.
Namaskaram, sir.
So,
Mr. Madhav garu, Krishnarao
Yeah.
CBIT నుండి.
Okay,
Krishnarao from CBIT, Hyderabad.
okay, right.
Right, sir.
How are you? Bagunnara?
బాగున్నాను
Right.
సార్.
Thank you.
Thank you.
Okay then. Huh? Have a good day. We'll see you on Friday.
thank you very much, sir. We look forward to your
Very-
interesting lecture on 5th, that is new perspectives on bearing capacity, sir.
Yeah.
So it will be very useful and very updated information on bearing capacity participants will get, sir. Thank you very
Sure.
much.
Thank you very much. Have a good day.
I thank all the participants for their active participation in the morning session. We'll meet again in the evening at 3:30 for a lecture on dynamic pile load tests. That is, we'll also have what are the various non-destructive testing methods available for piles, right, by Ravikaran Vaidya of geodynamics, Vadodara, right? So all of you join in time so that we can close the session in time, right? Thank you all. Have a good day.